Okay. Henderson-Hasselhoff equation today. Henderson-Hasselhoff. Bach. All right. So, the other day, I gave you, okay, let's just start again. When we do our Ka expression, this is usually what we get. Correct? You have, your acid is going to give off a proton and a conjugate base. And you're starting with your weak acid. Right? This is the format that we've been doing for any weak acid problems. Okay, then the other day what we did is we took that and we solved for the H plus. Yeah? Okay? Well, let's say we have a theoretical problem. 0.1 molar HF with 0.3 molar NAF. And the Ka is plug into our ice table, and because we're talking weak acid, we can eliminate the X's. So when we would plug this in here, all so far? Okay, we would have removed the X's. Okay, this would be how we would solve for our X if we were doing our typical ice table stuff. Fine, H plus, concentration when you solve that. Negative log of that is let me do that for me. All so far, just a quick review here of what we've been doing. Now I'm going to show you an even quicker way. Essentially, this is the format we're looking for. Remember, this would be our X if we were doing an ice table. Okay? And this is what it ends up being. Well, how would you get this to be pH? What would you have to do to that? Yeah, what'd you say? Negative log, okay? Well, since it's an equal expression, what I'm going to do is I'm going to take the negative log of everything. What's the negative log of this? What's the negative log of H? What's the negative log of terpan? All right?
You want the...
What's the negative log of Ka? What's negative log of terpan?
Negative Ka.
What's negative log?
Pka.
Yes.
Get done there.
Okay? Now, there's some rule with log-based things. I'm hoping you guys can clarify this rule. That when you take the log of two things that are multiplied, it's like adding them or something like that. There's some rule. I just don't remember it.
Which is 10 to the, it's 10 to the negative power of. So yeah, the powers are to add, right?
I don't know. There's some rule. I don't remember the rule.
The rule for exponents, if you do like 5 to the third
Because technically,
times
if you
5
take
to the
negative
fifth,
log of this,
5 to
it's
the
like
eighth.
you can add them. It's
Yeah.
some weird rule. I don't know
Yeah.
exactly how that
Well,
works.
it's like 5 to the third times 5 to the 8th. That's 5 to the 11th. You can add the exponent. That's how you multiply it, right? Am I right in that?
Sorry, I wasn't really listening that closely. What were you saying?
Like 5 to the third power and then 5 to the 8th power. If you multiply those together, it's 5 to the 11th power.
Sure.
So it's, you add the exponent.
Yeah, but I'm talking about log. So what I'm saying
Well, it's the
is,
inverse of that. So
we're taking this and doing log of both sides. What you get is this when you do it. So what I'm saying is how does multiplication, when you do log, come out to be addition and subtraction here? There's some rule, I don't remember it. You guys don't know it?
it sounds vaguely.
No? Okay. Well, there's a rule. I didn't just make that up. I just can't remember what the rule is for doing log. Okay? So, first off, pKa is just the log of, negative log of Ka. So you want to write that in somewhere, do it. pKa
I feel
equals...
like that isn't.
It will be interesting. Okay? Now, I'm going to make this simpler. There's also another rule that I don't know real well. It's been a while since I've done math. But I can make this positive sign if I take the reciprocal of that. That's some rule, but I don't know it. There's your Henderson-Hasselhoff equation. Right here. This is the buffer equation. Alright, so here's how I would do this. Looking at these guys, pH, someone take negative log K quickly.
It is 3.14.
3.14,
Yeah.
okay? Plus log of my base. My base is going to be the 0.3 over 0.1. Solve it, what do you get?
Log 3.
What?
I don't know if that's what you do. 3.62. Yep. It
Do you want to do titrations without doing that? Trust me.
3.62.
Now, what did we say governed the pH when we're doing buffer solutions? Last section.
The amount of buffer solution. There's an out there? Or is that not something
I'm sure there's something bolded in here.
Oh, the strong base speed. Oh, the amounts of HA and A minus versus present are very large compared with
Yeah, you need that. I'm surprised it's not in there. What governs the pH is the ratio of your components. Right there. Now, to make it a good buffer solution, we tend to want to have the components numbers high and relatively the same. But what governs the pH for a buffer solution is the ratio of your conjugates. Now, I don't know why it was on the screen yesterday, but I guess I didn't put it in your notes. I'm not 100% sure why it didn't get put in your notes. So, let's do a problem. Okay? You can use the Henderson-Hasselbalch equation when you know the ratio of your buffer solution. So I want you guys to solve this problem the old way. Do it the old way. And I'll do it the fast way in 3 seconds. Do it the old way. Do it the old way. It's just with sodium and that. Do it the old way. If I see any cheaters doing it the new way, I'm mad at you. What's HA? Talking about that? That's just a generic hydrogen defined weak acid.
Hydrogen and then A is like a variable.
A minus is a generic way for the conjugate base of that weak acid.
There are no.
It's generic. So like
There are elements which is
HF would be your weak acid. F minus would be your conjugate of it. The acid with the hydrogen, the conjugate after it's given up. Now I want you to go back and do nice tables here, all that fun stuff.
What is sodium lactate? Is it just that's one we have to know?
Sodium lactate's right there.
Oh, okay. It's the same as lactic acid, but sodium instead of the hydrogen. Okay.
It is the salt that gives you the conjugate of your lactic acid. That an answer? What? We can do it the long way. Okay, initial concentrations of my acid, 0.75. Initial concentration of my base, 0.25. Minus X, plus X, plus X. 0.75 minus X, 0.25 plus X. We go over, we plug it into our equilibrium expressions. Our K is 1.4 times 10 to the negative 4 equals my X over, or times 0.25, because we removed that X. And we remove that X, so 0.75. When we solve for X, we take and we multiply and divide. I don't know that off the top of my head real quickly. So.
Well, it'd be. You could also do X over 3. This 0.25 is a third of 0.75.
Yeah. Do you guys get 0.00042 for your X? Yeah?
Yeah.
Negative log of that.
3.38.
Is that what you guys got for your pH?
Yeah.
That's what you meant by the old way?
Yeah.
I thought you meant like doing this and then converting it to log for its pH after, instead of doing this.
Alright. Even then, it's similar, I suppose. I mean, that's where the Henderson-Hasselbalch equation comes in. However, when we start doing titrations and we're doing different points along the buffer system, this equation is going to be easier. So what you're going to do, If you use the Henderson-Hasselbalch equation, you're going to get a pH. You're going to take the negative log of your pKa. That is 3.85 plus log of your base over your acid. There's your base, 0.25. There's your acid, 0.75. Solve, you're done. Yes, did this equation come from that? Yes, it did. So you're saying if you use this, it's about the same.
Yeah, well, I thought you were saying that the Hasselhoff one, or Hasselhoff, was a lot easier than that one.
They're probably pretty similar.
Yeah, I didn't know you were saying it's easier than that. That's true.
Okay. I mean, really, what you're doing here, you still have to take the negative log at the end, so you really do have one more step once you get that. You did it wrong?
So,
Why?
so,
You didn't get, when you took the log of 0.25 over 0.75 plus 3.85?
I already changed the negative somewhere in there.
Okay.
So it was larger.
All right. So now this is going to be specifically buffer solutions because we said a buffer solution is going to depend upon this ratio. The higher that ratio, the higher those numbers are, and the closer that ratio is to 1, the better buffering capacity it will have. Okay? So we talked about earlier. Okay, I want you to do this one just a quick way because at this point, ooh, I may even want to show this one to you. Why do I say that?
Buffering.
Because it's got KB in it.
When you just do KW.
Yeah. But not all of you like to do it on your own. There's a few people in here that would just prefer to sit back and watch me do it. Okay. So I want you to stop and hopefully you can make some connections here, or everyone's working. Okay, go for it.
Already buffered, is that why it's different? Buffer times 10?
No. I don't know why it doesn't just say a buffer solution. Because technically this is just creating a buffer solution. We haven't buffered anything. What would I have to do to say I'm buffering something?
Adding more.
Add an acid or a base. Because we would want it to buffer to resist the change in that pH. Leave for an answer.
9.05.
You did negative log. 0.25.4? Okay, quickly, I want to show you, when you're looking at this problem, I want you guys to stop so you can, I want to show you this quickly. First of all, it says the buffer solution, tells us the components of the buffer solution. You need to be able to be good at identifying what's the acid and what's the base of this. We're a couple chapters in now. Have we seen NH3 a lot?
Yes.
Yes. You need to be able to quickly identify that that guy is your base. Or essentially, you need to find the conjugate pair. This and this are your conjugate pair. Just looking at the conjugate pair, which one has to be the acid? NH4. Okay? Well, we know that our Henderson-Hasselbalch equation has pKa in it, which means we want the Ka, right? So we are going to quickly change your Kb into your Ka. What was your Ka? 5.6.
That's a big deal.
Okay, I'm just going to quickly make that negative log of this. What did you guys get when you took the negative log of that? Okay, so pH is 9.25. Log of my base over my acid. What's my base? And my acid. Now the reason why we can use these numbers is, don't you remember that we're assuming that the x's are so small that it doesn't affect these numbers, right? Because technically at equilibrium, is it actually these numbers? No, but the equilibrium concentrations are so close to those numbers that we're going to get a good enough approximation to work. Okay? Now, last type, this is what we're doing here is going to lead us into doing titration problems, which are coming up soon. Same problem, except now we're taking and adding what to the buffer solution? A what? A strong acid. Okay? So if you remember yesterday, when you added something strong to a buffer solution, there was something we had to do before we did the ice table, or now before we do the Henderson-Hasselbalch equation. We had to do the stoichiometry. Okay, if we're adding an acid, remember that the acid is going to react with the strongest base present. What was the strongest base present in the previous problem? O plus. Add nothing. And we said the purpose, or the thing that makes it buffering resistant change in pH, is we're taking this strong acid and we're converting it into a what? Weak acid. So we still have to do the stoichiometry, and remember we're assuming what? We're assuming that this reaction is going to go to completion because this is an extremely strong acid that it will react to completion. So, in the previous problem, so this would be our stoichiometry step here. Okay? What was the before concentrations of this stuff? 0.25. Now, we should have it in moles. Be careful, because we're going to get to some problems later on where they'll give you different volumes and you'll have to figure out moles, because we cannot just take the molarity and always assume that it's the same moles. For example, if they said a 0.2 molar solution, but you have 3 liters, you would have to figure out how many moles that would be. Okay? They said what? How many moles here? 1 liter, okay, 0.1. And here, what did we say, 0.4? If this were to react to completion, this would be my limiting reactant, correct? Follow it. I've taken all of my strong acid and I've converted it to weak acid by using some of my weak base. Alright? Now, we can plug into our Henderson-Hasselbalch equation. pKa stays the same, it just changed the ratio slightly, didn't it? My ratio is now what?
0.15 over. Or 0.73 is
What was our pH to begin with?
pH. 9.5.
So you're probably thinking, that's a decent change in pH. Well, absolutely it is, because if you think about it here, guys, what we have is, we had a pretty large amount of strong acid, like almost half as much as weak acid, or weak bases we had. And our ratio wasn't 1 to begin with, right? But even then, you only changed it approximately 0.3 on the pH scale. If you were to take and add 0.1 moles of a strong acid to water, what's negative log of 0.1? What would that do to the pH? Do you see how if I took that strong acid and added it to water, the pH would be 1, but since I had the buffering components to it, all I did was take my basic buffer solution and lower it by only 0.3 instead of 6 whole factors, or 6 whole base 10.
Is there a unit for pH?
Well, it's based on,
pH of.
yeah.
You couldn't say it went down 6 levels.
Yeah, because remember, log is base 10, so
Right.
like, it, I mean, 0.3, it's actually log base 10 of 0.3, but still, yeah. So, questions on this. When you have, in your added an acid or a base, you've got a reactant to completion, and then you can do your Henderson-Hasselbalch equation. Just make sure you be very careful. Could I have added a base? What would have the base reacted with? This. So you would have started with this, reacted it, and you would have had to been a little bit careful as to what was the base component, what was the acid component when you plugged into your Henderson-Hasselbalch equation. Okay? Alright. Please use this equation though, because we're going to use it a lot in the next couple days.